Hi everyone. Thank you for inviting and sharing and having a platform for sharing some interesting ideas about what's going on in the field of 3D world reconstruction, neural world building, and so on. My name is Oles Petriv. I am a CTO of Reface and co-founder. And for the last more than 10 years, I'm actively experimenting with different 3D reconstruction pipelines and also with different natural language processing methods using machine learning. That's why I'm very excited to share some my and not only my ideas of where we are going in a domain of world representation for computers. My talk is why Gaussian Splatting is a new neural imagination engine. Some abstract words, but let's try to break it down, and let's start with what types of 3D data representation exist. As you know, to model and represent some 3D objects and parts of real world, or to create some computer game or VFX, you need somehow to represent 3D data on a screen and create some data structure that allows you to model all 3D features of 3D objects. And there are plenty of different approaches to represent 3D structures, like point clouds, meshes, graphs, multi-view fused images, octree, volumetric fields, sets of 3D descriptors, pseudo 3D and 2.5D projections of RGBD images, like RGB images with depth information, and different blends of these types of representations. You definitely know what is mesh, like set of vertices and structure of connectome of these vertices that allows you to represent 3D object as a set of triangles. Most of gaming area and 3D editors and so on uses this mesh representation as a baseline for 3D modeling, and then texturing it. And any computer game that you know consists of plenty of different meshes painted by textures. Each of these 3D object representations have their pros and cons, but in an age of neural networks, where for any task we have some sort of neural network that allows us to do some type of magic, most of cons of these types of data representations usually creates problems where we're trying to train neural networks on, for example, on a mesh data. Why? Because, for example, if you have a 2D image of fixed size, you can easily fit this image into convolutional neural network of fixed input size, for example, and then output some prediction detections, whatever. consistency of data representation is pretty crucial stuff when we are talking about neural networks. And mesh data is not very structured and consistently structured to feed them easily into neural networks like convolutional neural networks. There are plenty of different approaches how to transform this usual data, 3D data representation in a form that will be feedable to neural networks. But when we're talking about inverse problem, like when you have an image and you want to recreate 3D data representation that will allows you to reconstruct this image, but in 3D. Usually, classical approaches for 3D data representation are not the best way to represent data. So, really big leap in the field of 3D world reconstruction was the concept of neural radiance fields. What is neural radiance field? If you have a set of images captured from one real space around some real object or on a real street, whatever, you have a set of 2D projections of actual 3D space where each point on a 2D surface of each of images is a projection of a light field in a 3D objects that are conditioned on a 3D object that arise this light field. So if we have two images from different points of view, and we know from which point of view these images have been captured, we can estimate trajectory of light beams that projected on these pixels. And if we know this information, we can train a neural network that takes X, Y, and Z coordinate and angles of viewed direction as an input. So we have a five-dimensional input X, Y, and Z, and two parameters of view angle. Feed this input into neural network and train this neural network to output RGB and opacity parameter as a result of inference of this neural network. So if we have a consistent set of viewpoints from real 3D space, and we know which projected pixel is, and we know colors of each of projected pixels, we can transform these pixels as a result of ray projection, train a neural network that takes X, Y, and Z and view angle inputs and get a RGB and opacity output of this network. Pretty straightforward idea to capture underlying 3D structure of light in some 3D area as a neural network that somehow approximate behavior of light in the form of parameters of neural net. And this idea, it just works. It firstly allows us to model extremely real life looking reconstruction of 3D objects. And original paper of neural radiance field creates something like big boom in an area of 3D reconstruction and fusion of existing methods of photogrammetry with already existing methods of training neural networks. After aggregation of visual data from each point of view, we are able to train reconstruction like this, which is pretty amazing. And it is way better that the best results of previously state-of-the-art methods of photogrammetry that are using different mesh approximation of surfaces and trying to estimate texture on this surface. Because in a concept of neural radiance field, we are learning the whole light field with all information, how light behave from different point of view, and so on and so on. So what are cons of this original idea of neural radiance fields? It's training time, inference time, and whole list of performance questions. Why? Because to reconstruct one specific pixel of a resulting target image, we need to aggregate sometimes hundreds of points along the ray, then fuse this result to get just color of one pixel, and remarching neural network for hundreds of times for each pixels is pretty time consuming and computation consuming. So first generation of neural radiance field neural networks was pretty slow in training. Sometimes it can take up to few days or at least tens of hours of training on pretty high-end GPUs. And then it can take up to seconds or even minutes to reconstruct one frame. Usually seconds, but still very extremely slow. And after 2020, hundreds of different papers, different approaches that provides some optimization ideas, how we can speed up process of training, how we can speed up rendering speed and minimize compute costs have been provided. But the most brilliant and effective way to approximate these neural radiance fields while providing extremely low training time and extremely high rendering speed was Gaussian splatting. What is Gaussian splat? Gaussian splatting is a way of representing radiance fields of some sound, not by training neural network that will estimate RGBA parameters for each point of space, but by approximating this light field as a set of Gaussians in a 3D space. So we have Gaussian in a 3D space with a set of parameters which allows us to rotate this Gaussian, deform it in any direction, and modulate opacity and density of these Gaussians. So by increasing number of this Gaussian in this 3D space, we can approximate pretty correctly a lot of different shapes and light patterns. So instead of training one big neural network for whole SEM, we are estimating during training parameters for thousands or even hundreds of thousands of different small Gaussians. Each of these Gaussian estimate only small easily describable part of 3D space. So some complex SEM from that we are observing can be approximated as this blend of hundreds of different Gaussians. And the objective of training is to shift positions of this Gaussian, modify rotation parameters and opacity and colors parameters to match the stand that we are observing. If we will add to this Gaussian not only global RGB parameters like global color of Gaussian, but instead parameterize viewing angle and color as a spherical harmonics, we can model not only global color but behavior of color radiance from different point of view for one specific Gaussian, and set of parameters for spherical harmonics, position, rotation of Gaussian allows us to reconstruct extremely correctly and close to input an image. So this is the image of reconstruction of input image, and it is extremely close to the input, while it is just blend of hundreds of thousands of these Gaussians. While Gaussians are pretty fast to train, it took like up to 20 minutes on a modern GPU to fit model extremely well to set of 2D observation and get 3D reconstruction of a scene. It represents the stand as this blend of Gaussians. Each of Gaussian is explicit part of information, so you can easily edit, cut some part of the scene out of it, or shift or transform as a visual point cloud. So all existing method for editing and analyzing point clouds applies to Gaussian splatting, while also you can render it as a extremely well detailed image. So as a result, you can get such pretty nice real life looking reconstructions that are rendering with extremely high speed of hundreds of frames per second instead of few seconds for frame, comparing to original neural radiance field paper. So what's next? Okay, right now we have pipeline that allows us to reconstruct extremely well 3D model of light behavior on the sun by approximating it with this set of Gaussians. What's next? Next, we can try to model temporal the dynamic of objects with 4D Gaussians. If we parameterize these Gaussians not only in time, but not only in space, like X, Y, Z, but also in time, and learn some conditioning function that allows us to project 4D Gaussians into 3D space and then render them as 2D Gaussians on an image plane. We can model dynamic behavior of dynamic objects that have dynamic shape in time. And plenty of interesting ideas of how to parameterize them arise from last year. One of such approaches for the Gaussian splatting, but also there are something like up to 10 pretty impressive papers and works that allows you to model video as a dynamic of evolution of these 4D Gaussians and render each frame of a 3D video extremely fast. And as a result, if you have multi-view cameras, you can model 3D motion of each of a frame, each of the particle of which sand consists, and analyze dynamic of these 3D parts of the object in a pretty natural way, because actually we all consist of some subatomic particles that are involving in a 4D space. So Gaussian splatting with time condition model actual behavior of a matter. In Reface, we are working a lot with different face editing, and not only face, but usually face editing stuff. And one of the extremely interesting paper, Gaussian avatars, something around half year ago, create a splash in the area of 3D human modeling and 3D face modeling, because if you have a 3D mesh of a person reconstructed by any existing 3D mesh estimation pipeline of human face, you can sample different Gaussians on the surface of this mesh, then fine-tune these Gaussians on a real-world capture of the human, and then use this parametric 3D model of a face as a proxy to modify and edit actual RGB image of human face, which will result as 3D Gaussian avatar of a human, with full set of control on the head pose, expression, and so on and so on. After this Gaussian avatar paper, plenty of derivative works arise, and right now there are up to 50 different papers and works just in half year that utilize 3D Gaussian splatting on top of some rigged mesh of a human, of a face or even full body, to create and animate dynamic 3D avatar of a human with astonishing quality of appearance. As I know, no fully fully meshable model can achieve right now visual fidelity as close to real capture as Gaussian splatting provides. But usually you need to have information about your cameras, like to reconstruct, for example, this human model. You need to know specific parameters of your camera at each frame, angles, field of view, and so on and so on. Usually it is done by processing original image, original video through some structure from motion pipeline, or manually calibrating camera in specific environment, like some lab with calibrated cameras. But what if we want to have some reconstruction of the 3D world without knowing specific parameters of camera and their position at each space, time and space moment? The only way is to use soft structure from motion software like CallMap, which can be pretty computationally heavy. For a large sense, it can take up to 10 or more hours on a high-end GPUs to estimate position of camera. But in last 2 months, more than 5 interesting papers, and by the way, with code, all links are available in this presentation, comes out with a pretty interesting and impressive result that allows to reconstruct Gaussian splatting model of real world without knowing without originally knowing specific camera parameters, and without using this computation heavy pre-processing step of CallMap or other structure from motion pipeline, by integrating additional neural network that estimates and updates potential camera position into training pipeline of this reconstruction method. So right now there are methods that allows you to reconstruct part of real world in less than 10 seconds as a set of Gaussian splatting, and it is huge leap comparing to what we had even half year ago. Okay, we can reconstruct different parts of real world extremely fast and with really big, really high visual fidelity. So what's next? What the point? Why am I talking about some imagination engine and so on and all this stuff? to model the world, we need to understand it. We need to be able not only to synthesize some visually appealing set of pixels that looks like what our eyes see, but to transform this set of pixels into world model, we need to understand what type of objects, what semantic structure of part of the world that we are observing, and how from what it consists. And one of our tools to understand world is our language. We decompose these visual textures and all we see into a set of words, and then we map these words to some part of this visual observation that we have, and fusion of all this stuff transformed into world understanding that we have. So one of the most interesting research in the last time is the length splat. This approach extends idea of Gaussian splatting and fuse the idea of Gaussian splatting with a set of works that uses language supervision with computer vision tools and utilize feature vectors from computer vision neural networks that map different part of input image into some high dimensional abstract vectors that are highly correlated with some abstract or not abstract words from human language, which allows us to map meaning of this part of pixels into some highly abstract thing like word. And as a result, if we back project these semantic features into Gaussian splatting, not into Gaussians, not into pixels, we can learn a semantic field where each object, each part of a input image represented as a blend of 3D Gaussians with semantic meaning fused to these Gaussians. And it allows us not only to model through the world and render it such model extremely visually nice, it allows us to understand. It allows us to make semantic search on the image, to analyze what part of this particular 3D scene is food, what wooden part of this scene and so on and so on. But also it allows us to model different attributes of this world reconstruction model. And
I'm so sorry to interrupt. We also have 2 minutes left.
Okay. So by utilizing semantic information about this external world model, we can create simplified version of all 3D objects, fuse semantic meaning of this 3D objects into some simulation parameters, and by fusing 3D Gaussians with these invisible proxy mesh models that have dynamics derived from semantic meaning, we can model how part of this world model will behave based on these estimated parameters, as like we humans do in our brain world models. So right now, we have extremely fast rendering approach to model external world as a dynamic, high fidelity looking, with semantic meaning, 4D or 3D model that are that trains in native ways for neural network pipelines, which allows us to create semantic fields that are extremely feedable to any type of neural network that we have right now, which allows us to edit, modify, and synthesize any potential stand. That's why I think Gaussian splatting is the core part of next gen AI models of the world that are modeling world in native 4D manner with some abstract semantic meaning that we humans do, and model even potential changes into this 3D and 4D reconstruction of the world. So I cannot name it other like imagination machine, because this set of texts that arise this year have all necessary parts to be able to visualize, model, render, modify, and this is imagination from abstract words or from visual input.